Okay. Good morning, everyone. Welcome to our last week of classes. So from a good number of people, we've have nailed down what their final presentation is going to be about. There's at least a couple people that we're still emailing back and forth. And yeah, I'm continuing to check my email, and we'll be in contact if I haven't responded yet about your presentation idea. Sorry. Okay. So for the last few days, I want to talk about another important type of mathematical model, which is especially relevant, and this is about exponential growth, or things growing exponentially. So we think a lot of times we're kind of in the way that it gets used, something growing exponentially kind of just gets interpreted as it's growing a lot. But exponential growth does have a very specific mathematical meaning. And it is something which grows very fast, but we want to kind of be more careful and precise about that in order to talk about different speeds of exponential growth, and to how you can actually measure how something's exponential growth. Okay. So what we talked about before, what we spent a while going over, is that if something is growing linearly, that means that over some amount of time, it increases by some fixed amount. So this is something, some population increases by 500 every year, or 500 every week, or something like that. So their just raw amount is fixed. And over every week, no matter which week you're looking at, if you go from one point to a week later, it goes up by that fixed amount. Something grows exponentially if the quantity is increasing by some fixed proportion. So these are a little out of order, but the proportion part here this is something like it triples every day, or something is cut in half, or triples every week, or is cut in half every 2 days. So here, you're not told how, like the raw numbers it increases every week or every 2 days, but you're told there's some proportion or multiple um, that you get going from 1 week to the next week. Another way of describing this same way of growing is exponential growth is when the amount your quantity increases is proportional to that quantity. So saying something is proportional, meaning you've taken your quantity and you're always multiplying by some fixed number. As in the second example here, something is cut in half every 2 days. There, your quantity is being halved, so it's not growing exponentially, but it is decreasing exponentially, or sometimes that's called exponential decay. So a lot of times, especially populations, they're growing exponentially. But if something is decaying exponentially, we're going to use the same type of function in a lot of the same terminology and kind of mathematical machinery, but it's not just things increasing. And if we're looking for, we did encounter something like this previously. We were talking about given a sequence, so given some list of numbers, try to find a pattern. And we encountered something which was a geometric sequence, which was you have a list of numbers and to go from one to the next, you keep multiplying by some fixed number. That is exponential growth. So we won't be doing anything with this, but just to see some examples that had showed up already, we use this other terminology. But a geometric sequence is really only taking some list of numbers, and we're going to be wanting to look for functions that take any real number in as an input. So we'll be looking through a bunch of examples where this is the way that growth is described. Not the amount is increasing by some fixed amount, but there's some proportion we're looking for, which tells you how to go from one quantity to the next quantity after an interval of time. Okay. So this is kind of a lot, but the kind of main point is that exponential growth is really appropriate when you're talking about population growth. So this can be, spread of a disease, or population of some animals, or population of some city. In a lot of cases, exponential growth is really the right way to model a population increasing. With the idea being that you're wondering how fast is cities growing? And there are a lot of ways that cities can grow. People moving in, you also have to worry about like people leaving or dying. So there's a lot that goes into how does a population change? But suppose you only focus on number of births. So you're kind of ignoring a lot. And so that makes this situation not really realistic. But if you're thinking about just how many new people are being created by the people that are already there, the point is that the number of new babies depends on the population, but in a very predictable way. So the situation is that big cities are going to have more babies than small towns, not because there's something about large cities that gives rise to having more babies, but it's just within a large city, you just have more people, and those people and that larger number of people will give rise to more babies than the smaller group of people can. So they're not behaving differently, just there are more people there to potentially have babies. And this same kind of phenomena happens if we're talking about a very different kind of population growth. So imagine that you have a petri dish in a lab and you're growing some single cell organisms. How these organisms reproduce is that there is one cell and then they split into two identical single cell organisms. And this case, we really see that well, so here's the takeaway line is that populations double after every cell splits. So this is the mechanism each single cell splits. That's how how these things reproduce, no matter how many of them you have. So every single thing is behaving in exactly the same way. But if you have a larger colony, after everyone's done splitting, you'll have double that colony, which is just, as far as raw numbers there, you'll have a bigger increase than if you double a smaller number. So numerically, this is saying that if you have cities of these two different sizes, 2,000 and 10,000, or this could also be, well, we can recycle these numbers for this other example too. If you take these and you know that your population is doubling over a decade, then the first one doubles to 4,000, the first one doubles to 20,000. And even if you assume that the people in these two towns are having babies at the same rate, just there are more people here to have those babies than there are here. And so you're going to increase. And so this idea of proportional growth gets down to, you don't want to just measure raw numbers. So you wouldn't want to think, or linear growth would say over a decade, no matter where you start, you're going to increase by the same amount. But for populations, that's not exactly the most natural assumption on growth. Kind of how many people you get depends on how many people you actually have. And so exponential growth is really common for populations. So before we kind of see some specific mathematics stuff, do you guys have any thoughts or questions on, or anything I can clarify on this, why exponential growth, the amount that you increase by, depends on how much you have, why that is a good sort of assumption on growth for populations. So for populations, exponential growth is good because saying if over a decade you're going to increase by 2,000, that's doubling for this size, but is increasing really slowly if you already have 10,000. So you want the amount to depend on how much you have, and that's exactly what exponential growth is all about. So we want to think about what models for exponential growth looks like. What function can we write down, which gives us a formula that lets us answer the types of questions that we had been talking about, using that to predict the population or the quantity at a certain time, or find when a quantity reaches some certain threshold. So talking about populations, suppose you have a rabbit farm, you're starting with 10 rabbits and the population doubles every month. So what does the population look like over the first few months? And you starting with saying month 0 is before, or when you get the rabbits and you get your 10 rabbits, we'll call that month 0. So before any time has passed, that's month 0. Well, if we want to know what's happening every month, we know we're starting with 10 and we keep doubling. So doubling is just multiplying by 2. 10 doubles to 20, that doubles to 40, that doubles to 80, that doubles to 160. So after 4 months, you have 160 rabbits, which is a lot of rabbits. A hallmark feature of exponential growth is it grows really, really fast when you keep doubling. So talking about number of COVID-19 cases increasing exponentially, things get really big really fast when you're growing exponentially. And actually, right here, I had a kind of anecdote I want to pull out. So we'll come back to this. But a kind of parable which really says exponential growth gets really big really fast, and often a lot bigger and faster than you think it would. So where are we at? So here's a story. So the legend of Pal Pai Sam. This is some Indian rice pudding. So there's a legend, and it goes is right. So kind of the origins of the tradition of serving this rice pudding to visiting pilgrims. So the idea was that there was a king. He's a big bigoted playing chess, and someone came by and challenged the king. And the king offered any reward that the traveler could name. So maybe surprisingly, the traveler said he wants some rice. How much rice he wants is, if he wins, clear the chessboard, put 1 grain of rice on the first square, 2 on the next, 4 on the third, and keep doubling that until you fill up the chessboard. And so through the first 3 squares, that is 7 grains of rice. So the king says, sure, that sounds fine. The thing is, the king loses, and then they start to compute how much rice you have to give this person. So there are 64 squares on a chessboard. And if you start doubling, you see these numbers. This is 500,000. That doubles to about 1,000,000. Here is 500 million. And so these numbers just keep getting bigger. So if you actually compute these numbers, on the 20th square, you're going to have to put 1,000,000. That is here. On the 40th square, which is here, that is a trillion. So 1,000 million. No, that's billion grains of rice. 1,000 million billion. Yeah. And on the very last square, you'd have to put 18, let's see, 1,000 million billion trillion. It's like sextillion or something like that, which, okay, is 210 billion tons of rice going on the very last square. So that in addition to the rest of the board. And so where the legend comes from is that's more rice than there was rice. And so then the Krishna revealed their identity and said, you can do this, you can pay the debt over time. So that's why people are still being fed. Pilgrims are still being given this rice. So it's kind of an interesting story, but also says the exponential growth is crazy. You're starting with 1 grain of rice and you're doubling. And by the end, you're getting just so many zeros, 210 billion tons of rice. So much so that when I was looking this up a little bit, using Wikipedia, and as a, this is maybe bad to say, but for mathematical topics, Wikipedia is really reliable. People just don't go in and want to change it. So that parable is really called this wheat and or rice and chessboard problem, which is how many pieces of rice do you have? An interesting variation is, would you rather have $1 million or start with a penny and double it every day for a month? And the answer is you should take the penny doubled every day. And so one thing I thought was, so this tells the story that, or a variation of the story that we saw. There is the sum of this kind of series is something we can understand mathematically, and we get the same numbers here. But what I thought was interesting is this phrase, the second half of the chessboard, which is really saying you're filling this chessboard up, and the amount on the first half is just minuscule compared to the second half. So the number of grains on the first half is 4.3 billion. No, I'm off. 4.3 million, right? Hundreds, thousands, million. No, right. Yeah, 4.3 billion. So 279 tons just on the first half. Um, but as soon as you go to the next half, um, the second half contains just so much more. In fact, this first square um, over here um, contains about as much as the entire first half. So when something grows exponentially, when you get um, further out, um, the amounts you're looking at are just so much more than the first half. So when something is growing exponentially, it doesn't seem so bad at first, but the numbers are just staggering when you get far enough. And the numbers in here, this is doubling and it's going up to 64. That's not a very big exponent. So after 4 months, you have in this example here, get back to here. After 4 months, you have 160 rabbits, which seems like, that's kind of a lot. If you kept computing, by the end of a year, you're going to have way too many rabbits. But, okay. So we can tell you're going to get a lot of rabbits, but what's the formula here? So if you want a formula for rabbit population after T months, you're looking for some kind of pattern. And what we notice is in each of these, there's this 10 that we started with, and then these powers of 2. You could even think of this 10 here as 10 times 1, or 10 times 2 to the 0, which is, 10 times 1. So the pattern in here is there's always a 10, and then we have powers of 2, with the power being which month we're on. So 10 times 2 to the t is the formula for this exponential growth. And actually, let me right. And just to see how many rabbits you'd have at the end of a year, you would have 40,900 rabbits. So 40,096 is 2 to the 12. So after your 12 months, times the 10. So after a year, you would have almost 41,000 rabbits. And that's saying exponential growth grows really quickly. And you really get into unmanageable amounts. So in general, what exponential functions look like is they're going to look like some number a times some number b, and this b is raised to k times x. So x here is the variable. A, b, and k are these constants, these parameters, where for different choices, they can give you different shapes. But, well, I guess it's all kind of the same shape, but they can change exactly how the graph is positioned, or exactly the points that lie on the graph, even keeping the standard exponential function shape. So this is the standard form. There's some constant in front, and then you have b, which is called the base. and that base is raised to a constant times x. These second two expressions here, this is just the way that we're going to write it. Sometimes I won't do the superscript. I'll just use the caret to say this is up in the exponent. What this second or this third thing says is using an exponent rule. So you have powers multiplied. That is equal to raising the base to the first power and then raising that to the second power. This is really just to say you don't often need a k here, or you don't necessarily need a k there. But sometimes it's useful to kind of have separated the base and this constant k, just to see how changing them changes the function. Even if you could just write it as some number raised to the x power. So in this case, a and k can be anything. B is always positive, but it isn't 1, and that's called the base. If k is positive and your b is greater than 1, then your function is going to be growing exponentially. Because if you're taking, and we'll see some pictures of this, if you have a number which is bigger than 1 and you're raising it to a positive power, those quantities are going to get bigger. On the other hand, if you have something less than 1 and you're raising that to positive powers, the quantities are going to get smaller, so that's exponential decay. In this case, think of taking like a half and multiplying a half by itself. A half times a half is a fourth, times another half is an eighth, times another half is a 16th. So you keep multiplying those numbers together and they end up getting smaller. And that happens anytime you have some fraction, and your k here is positive. The reason I mentioned k being positive here is if you let it be negative, then these two options flip. Taking a number like, let's look at some pictures to see exactly what these look like and how changing the numbers can change the form of the function. So, see, so basic exponential function 2 to the x. So this, in general, is what all exponential functions look like. So if we kind of go out here, 2 to the first power is 1. Okay, or no, that's not true. And I was pointing at the wrong point. 2 to the first power is 2. 2 squared is 4. We've got that point. 2 cubed is 8. That puts us here. 2 to the fourth is 16, so that's further up. So as we go out in this direction, our numbers keep getting bigger. 2 to the 0 is 1. And in fact, anything raised to the 0 is 1. So if you have this most basic exponential function, just a number raised to x, it always has the value 1 here. Also, if we're going the other way, we're getting smaller numbers. And this is how negative exponents work. 2 to the negative 1 is 0.5, which is a half. 2 to the negative 2 is a fourth. And we can see those numbers. Let's see. Yeah. Negative 1 puts us at a half, this one is right here. If we go to -2, we're at a fourth. So what happens is if we go out and have negative numbers, our numbers get smaller and they get closer and closer to 0. So here we have a horizontal asymptote where if you keep taking 2 and raise it to more and more negative powers, you're going to get smaller and smaller. You'll never actually reach 0. Um, zoom in it, we get closer and closer, but we never actually get 0. So we also want to think about how we can change this. So one thing that we can do, if we take that formula that we had before, is so that rabbit population was 10 times 2 to the x. What this number does is, well, originally at 0 we were at 1, but then here we've multiplied by 10, so now our function is up at 10. But looking at these are essentially like parallel. It's growing at the same rate, just this one multiplied by 10 is starting higher. So this 10 here really only affects the initial value. If we go back to 2 to the x, but we say look at 5. Now, if we put a 3x there. So one thing we said was we could have extra constants in here. So here we can see that this function is actually growing a lot faster. So this 3 here is what's responsible for having this exponential grow a lot bigger. Why this happens is if you rewrite this as a power to a power, you get 2 to the 3 raised to the x, and 2 cubed is 8. So these two are the same function because this 2 raised to the 3 is what gets you this 8. So keeping track of exponential functions, one way is that the bigger your base is, the faster you grow, which makes sense. If you're multiplying a bunch of 2's together, that's not as big as if you're multiplying a bunch of 8's together. But what's kind of nice is another way to keep track of that is leaving the base the same and just changing this constant k in here. So here it's just a 1, nothing there. Here there's a 3. If we were to change it even more, so 2 raised to the 5, let's go crazy, 2 raised to the 7x, that's even steeper. And if we were to go the other way, so 2 raised to the 0.03x. So you can also make it really flat by making this closer to 0. You can see it's still growing, but it just takes a long time to get there. Like at 150, this is still, below 10. And at 150, these numbers are just enormous. Or at 50, these are big. 150, this one makes it at least to like 25, and the other exponential functions are just huge. So we can keep track of how fast these things grow by changing that k. And rather than, um, or you could keep track of it by changing the base, but keeping these, by doing these Ks as the things that change rather than the base, it's easier to compare them and to kind of see exactly how they compare. Nope, wrong way. What's also worth pointing out is we go this other way, so 1/2 raised to the x. That's the same shape, but now it's reversed. So here, this is decreasing exponentially. And now all of the kind of computations we did are reversed. If you put in positive numbers, this keeps getting smaller because you're multiplying 1/2 by itself more and more. If you put in a negative number, you're flipping this fraction, which is giving you which will give you positive powers of 2. And we can also get this by saying 2 raised to the negative x. These two graphs are the same. So having either a negative k value here or having a fraction, those give you the same type of graph. And so this is the exponential decay. As you go out further in the positive direction, it keeps getting smaller and smaller. And especially in this case, there are some variations we won't really use. But we can also say if we add some number 6 to this. So one thing which really does kind of fundamentally change the shape is adding some number outside of it. So it's not multiplied, it's not in the exponent, it's just really outside there. And that moves your graph up. So this blue graph, you have something decaying and it's getting closer and closer to 0. Well, maybe you don't want something to decay to 0, but you want to say it's shrinking and it's getting close to some other value. Well, that's what can happen here. This graph keeps decreasing and it's getting closer and closer to 6. And the same kind of considerations before can happen if we tweak this. We can make it steeper. What happens over here, if you, let's just zoom in some. One half raised to the 0.4x. So here, changing this k again kind of changes the steepness, but it also changes the steepness with how it decays. So here, 3 means this blue thing gets really small really fast. Where this 0.4, on the other hand, is decreasing. It is going towards 0, but it's a lot flatter. So the same kind of comparison we saw here, the 3 makes us steeper when we're going up. It also is steeper going down. And the 0.4, the thing smaller than 1, makes us flatter going up, but also flatter going down. So here we have this basic shape, which is this exponential function and matches when something is growing by some fixed proportion. And changing these constants is how we can take that basic description of how the growth is happening and make it fit the actual points that we're talking about. Um, so how those values actually get interpreted. So we've seen that um, the A kind of shifts you up. The K depends on or impacts your steepness. Um, the A here is always the initial value of your quantity. So that was something that we saw. Sorry, let me go back here. Want these ones. So in these cases, the A here, the red and purple don't have an A, so they just go through 1. The green one does have an A, that's 10, and that's where we start with. So the quantity multiplied in front that doesn't have an exponent, that is how much you're starting with. And mathematically, that makes sense. Initial values correspond to putting in 0. So if you put 0 into this formula, well, you have A times B raised to the K times 0. So this X becomes a 0. Then the whole exponent is 0, and anything raised to the 0 is 1. So the whole exponential part, when you put in 0, just becomes 1. So all you're left with is the A. So this is one thing that we want to keep in mind if we're wanting to actually come up with a formula. If at some point we're told what is the initial amount, that is exactly the A that we're going to use in this formula. The B and K are a little more complicated and they kind of come together. The B you'll often take to be the proportional rate of increase. So this, I mean, something is doubling or tripling or being reduced by a factor of, or you're taking a tenth of it. That number is what you can take to be the B. And the K is the reciprocal, so 1 divided by the time it takes to increase by that proportion. And especially the second part needs an example. So here's a kind of question. Suppose you have a bacteria colony and it is very small. It starts with 5 bacteria. And because of the kind of bacteria that you actually have there, it's doubling every 6 days. So what is the formula for the number of bacteria on day T? So a general formula that tells you how much you have on any day at all. So what the formula will be is 5 raised to the 2t divided by 6. So where do these things come from? So the first thing, which isn't really written, is that we have something that's doubling every 6 days. That statement there is saying that that's how we know this is exponential growth. Something increasing by some fixed proportion over some interval of time. That is exactly what it means for exponential growth. Over this 6-day period, you see where you were and you double that. And so that's not kind of your new amount, depends on where you started, because you're doubling whatever you were. So this part is what says we know this is exponential growth. What we also know is we're starting with 5 bacteria, and the A, so if we know it's exponential growth, we know it looks like this, and we're told what we're starting with, so that's what our A is going to be. How we decide on the rest of it is we're told that we're doubling every 6 days. The doubling part says we were multiplying by 2. that's what says we really want we want a 2 to be the base here, because everything is being measured in how long or how this doubling is happening. So we want to be multiplying by 2s. Where this expression comes from is we're told the population doubles every 6 days. So what needs to happen is when we put in 6, we need to get 10, which is double what we started with. And so that's what this 6 here really is designed to do. It's so when you put in 6 into this formula, the exponent you get is 1. And so that gives us our extra factor of 2 times the 5 we started with to get the 10 that we were expecting. So that's what this reciprocal of the time it takes to increase by that proportion. You have the doubling time, doubling every 6 days. We want to divide by that. So when we put in that doubling time, we get exactly an extra factor of 2, which is exactly the doubling that we want. So we'll talk about some more examples Wednesday. So I guess between now and Wednesday, there was a assignment that was posted. I owe you guys a kind of video of me walking through that assignment, so that's going to be posted today. Also, if you haven't gotten or had an email exchange with me that essentially ends with "I approve," let me know if you have any questions. Make sure that you're in contact with me about your projects. And if you have any questions about what those projects are supposed to be, let me know and I'll be happy to answer them. But other than that, I can stick around if anyone has any questions, but if not,